Okay, now we look into the third part, which is the topic 2.3, central force motion and space mechanics. This is just a brief introduction to the space mechanics subject that we will learn later on in the next following semester. Okay, first we start with the angular momentum of a particle, where as we can see here, we have a satellite. Okay, the satellite orbiting the Earth. Okay, satellite orbits are analyzed using conservation of angular momentum. Okay, let's assume that this this point at A here is the satellite, and this point here is the center of the Earth. And as you can see, this particular satellite is moving following this red lines curve trajectory. Okay? And before we proceed further, uh, for satellite, normally we have our natural satellite, which is what we call moon. The moon is our natural satellite, and it is our man-made satellite. Okay? Okay, equation of motion in radial and transverse component, where we simplify the previous example into this. Okay, point P is here, and we have the normal component and also the radial component of the forces. Consider particle at R. Okay, remember that R at here, 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 at any point along this curvature is different. Okay, the R will be different. Okay? As theta is increased or decreased, is any change in the theta, the R will change as well. Okay, summation of Fr is equal to MAR is equal to M times in bracket, we have R double dot, which is the acceleration AR, okay, minus R theta dot square. Okay, this formulation, this one and this, we have looked on our previous lecture on how to derive these two. Okay. Okay, this result may also be derived from conservation of angular momentum. Okay, can also be derived from the angular momentum, where the angular momentum we denote it as HO. Okay, momentum at point O, respect to point O, is equal to mr square times theta dot. Okay, then you can further expand this part. Then finally you can see that summation of f theta is equal to m r theta double dot plus 2r theta 2r dot theta dot. Okay, then we have the moment of momentum or the angular momentum of the particle at point O, like so. We have here, okay, you have to be careful. Now we are dealing with the cross product. Okay, what does it mean? When you have a cross product, it's basically something to do with the vector. Okay, H naught is perpendicular to the plane containing R. Okay, and then M times V, this part here, or this part down here. Okay, and it is can be expanded like so here. Then look into the I, J, and K component. We have like what we have shown here. And the derivative of angular momentum with respect to time, you can do this process. Okay, I hope you are familiar with the calculus, so you can do the math of it. Okay, it's follow from Newton's second law that the sum of the moments about O of the forces acting on the particle is equal to the rate of change of the angular momentum of the particle about point O. Okay, conservation of angular momentum. When only force acting on particle is directed towards or away from a fixed point O, the particle is said to be moving under a central force. Okay, like this one. Since the line of action of the central force passes through point O, given like this, position vector and motion of particle are in a plane perpendicular to H. Okay, I hope with examples, it will clear up on, it will make it more clearer. Okay, magnitude of angular momentum, what we have is like this. Okay, okay, radius vector OP swap in fact infinitely small. Okay, just this shaded, the blue shaded region here. Okay, we assume it is very small. Okay, okay, dA is the area of this pipe. Okay, is equal to half r square d theta. Okay, and we can define it. We take the dA dt of it. Okay, then recall from a body moving under a central force, we have h equal to r square theta dot. Okay, which is similar to this. When a particle moves under a central force, its area velocity is constant. Okay, now gravitational force exerted by the sun on a planet or by the earth on a satellite is an important example of gravitational force. Okay, there is a force acting between the, let's assume this one is our earth and this one is our satellites in the space. Okay, Newton's law of universal gravitation, two particles of mass m and capital M and small m attract each other with equal and opposite force directed along the line connecting the particles. Okay, can be simplified like so, where g is the constant of gravitation. Value is like this. For a particle of mass m on the Earth's surface, what happens is, this is our gravitational acceleration that we normally use. Okay, for SI unit, and this one is if you use the US convention. Okay, now moving on, our first example for this particular subtopic. A satellite is launched in a direction parallel to the surface of the Earth with a velocity of 30,000 kilometers per hour. Okay, it's very fast. From an altitude of 400 kilometers. Determine the velocity of the satellite as it reaches its maximum altitude of 4,000 kilometers. The radius of the Earth is given 6,370 kilometers. Okay, so what to do? First on, okay, look at this image here. At A, it is 400 km. Okay, it is launched from here. Okay, and then we have at B, 4,000 kilometers. Okay, at point A, normally we refer to what we call is perigee. Okay, perigee, which is the nearest position when any particle is orbiting our Earth, for example. Okay, the farthest away at B here we call it a apogee. Okay. Okay. Now, we since the satellite is moving under a central force, its angular momentum is constant. Equate the angular momentum at A and B and solve for the velocity at point B. Okay, this is what we are looking at. Okay, determine the velocity of the satellite as it reaches a maximum altitude of 4,000 km. So we need to find BB. Okay, now from this formula that we have go through just now, the previous slides, okay, you can use this, and then since the momentum is constant, so anything at point, the momentum at A and momentum at B should be the same. Therefore, you can rearrange this particular equation like so. M is cancelled because the mass of the satellite is remain the same when it is at A, or at B, the mass is the same. However, the only difference is the RA and RB. RA is 400 km, RB is 4,000 km, and at point A, it is at 30,000 kilometer per hour. So from this, we can calculate our VB. So VB is calculated, and it is 19,590 kilometer per hour. Okay. Remember that when you want to calculate the RA and RB, you should also include the radius of the Earth together in your calculation. Okay. Okay, for particle moving under central force directed towards force center, so you can use this expression like so. Second expression is equivalent to R square theta dot, from which theta dot is equal to H over R square, and R double dot is equal to this part here. After substituting into the radial equation of motion and simplify, you can have this term here. If f is a known function of r and u, then particle trajectory may be found by integrating for u, okay, with constant of integration determined from initial condition. Okay, now consider the Earth satellite subject to only gravitational pull of the Earth. You may refer to this. Solution can be equated for this conic section like so, where you have this symbol here. That is represent the eccentricity. Okay, origin located at the Earth center is a focus of the conic section. Okay? So this trajectory may be ellipse, parabola, or hyperbola depending on value of eccentricity. So this particular value, this one, will determine whether it is a ellipse, parabola, or hyperbola. Okay. Now, trajectory of Earth satellite is defined by, okay, it is the general one. For hyperbola, it depends on if the eccentricity value is larger than 1, okay, the radius vector becomes infinite. Okay, this one is this particular line here. Okay, for the parabola, okay, this one and for ellipse. This one down here. Okay. Integration constant C is determined by condition at beginning of free flight. Okay. Condition at free flight. Launch using the rocket, suppose. Okay. Up to a point where we have our powered flight, then burn out, then start the free flight. Okay. If you notice just now, I mentioned about the 30,000 kilometer per hour. Okay, what does it mean actually? It looks very high. The value is very high because of that is the velocity, the relative velocity. Yeah? Okay, satellite escape Earth orbit from. You can use this particular formula to get the uh, uh, escape velocity. Okay, the minimum velocity to escape from this Earth orbit. Trajectory is elliptic for V naught less than V escape, and become circular for eccentricity equal to 0. Okay. Recall that for a particle moving under central force, the area velocity is down like so. Okay, then we look into this example, another one. A satellite is launched in a direction parallel to the surface of the Earth with a velocity of 56,900 kilometers an hour at an altitude of 500 kilometers. Okay, here. Determine the maximum altitude reached by the satellite and the periodic time of the satellite. Okay, okay. Okay, now we look into this question, determine the maximum altitude, finding R at theta equal to the maximum. This point is 180 degrees. With the altitude at the perigee and apogee known, the periodic time can be evaluated. Okay, now uh, we can first get the value of R naught or R0 is equal to this. This is the radius of the Earth plus this radius from A to the Earth's surface, 400 kilometer. So this is the value. Then calculate for the velocity, okay, V naught. So 36,900. Then you do the conversion. Then you get a 10.25 okay, power of 3 meter per second. Then calculate your H is equal to R naught, V naught. Then it is the value, okay. More or less it represent the, yeah, it is the H. Okay, GM, okay. Then that is equal to this. Then you use this particular value of this M, put it here, and it is your R naught, which is this one, and this one is your H. Okay, this is your H. Then you can calculate the value of C. Okay, then to get the value of R1, use this particular formula that we have shown before. Then can get the value using this particular formula, rearrange of course, because you want to get this R1. Then after substituting all the values, including the value of C, then you get this R1, the maximum altitude that this particle can reach. Okay. Okay. Now we have the value of the maximum altitude and the minimum altitude, the apogee and perigee. Sorry, not the maximum altitude and minimum altitude. Now we can get the time, okay, the periodic time that we are looking at. Okay, use this formula. Okay, the formula is given like so. We already calculate the h, but now we need to calculate the a and b. A is nothing but is equal to half r0 plus r1, and b is the square root of r0 or r0 times r1. Then just use this particular formula to get this total time. Thank you.